The electric field. Today we're going to be discussing electric fields, electric field lines, electric fields and conductors, as well as some relations between E&M and mechanics. Alright, electric fields. So the electric field is produced by a source charge and it will enact a force on another charge placed within the field. So what we mean by source charge is simply the charge in question. So if we want to find the electric field of this positive charge, the positive charge would be our source charge. If we want to find the electric field of our negative charge, the negative charge would be our source charge. If we want to find the electric field of both, they would both be our source charges. You can have multiple source charges, and generally it just means the charge in question. Now when we want to determine the electric field, we will use a small positive charge such that its force that it exerts is negligible. So in this case, you'll look to see that there is a small positive charge Q, and then our source charge, negative Q, and this small positive charge Q is called our test charge. A certain force is going to be exerted on our test charge by our source charge. And if we determine that force, we can then kind of draw our force vector, which you can see by this little arrow. And that's the force vector acting on our test charge, this small positive Q charge, by our negative charge. Now, to determine the electric field, simply we divide out our test charge. It's very confusing how we get to electric fields, but once you find out the equation is simply Coulomb's law missing one of the charges, it is very easy to work with. The electric field is going to go away from positive charges and towards negative charges, and this is because we use a positive charge as our test charge. So it's going to go repel away from a positive charge and attract towards a negative charge, right? And the electric field at a particular point in space is simply going to be the sum of all the electric fields acting on it. So if we want to find the electric field right here above the positive and negative charge, we would have to add the electric field from these two individual charges. That would be the total electric field. Okay, so next up is electric field lines, and for now we're just going to briefly discuss them and definitely get a lot more into them when we start discussing flux and Gauss's law. For now, we need to think of electric field lines as a useful tool for describing electric fields. So, as we just discussed, electric fields will emit from positive charges and kind of be absorbed by negative charges. Same thing goes for field lines. So if we look at this electric field line, it's coming out of this positive Q charge. And the density of electric field lines corresponds to how strong the electric field is in that region. So if we take some imaginary arc all the way to the left of this positive Q charge, the density of the electric field lines is very low. You can see they're very far spaced apart. And so we can kind of interpret that to mean that our electric field is going to be very weak. As we get closer, you can see that the density grows. There's going to be a lot less distance between each electric field line, and therefore we can interpret that our electric field is stronger. Now this agrees with Coulomb's law. If you remember from Coulomb's law, the force and therefore electric field acting on a charge is going to be proportional to 1 over the distance squared. And when you have 1 over the distance squared, we can expect that the strength is going to drastically decrease as we go away from the charge. Another thing about electric field lines is that they cannot cross and they cannot have multiple directions at a particular point. The electric field lines are always a statement about the net electric field there. You won't have two different charges and talk about their independent electric field lines if they're in the same system. So if we look right here, we have this positive charge and this negative charge, and we combine their electric field lines, right? We can imagine this negative charge as having all these electric field lines coming in towards it because negative absorbs electric field, right? But we have to combine that with our positive charge since these ones are in the same system. And so the electric field from the positive charge is going to go towards the negative charge. Similarly, over here, we have two positive charges, and so they're going to want to kind of give out these electric field lines just as up here, except they cannot both give out towards the center, right? They're going to give out, and then they're going to kind of interfere with each other to prevent themselves from crossing. That does mean that we can interpret there to be a point in between these positive charges where the electric field is 0, and you will call that from Coulomb's law. Okay, electric fields and conductors. So this can be kind of a tricky subject to learn at first, but in the static case, electric fields do not exist within conductors. A conductor will always have an electric field of 0 inside of it if no charges are moving. And this can kind of seem counterintuitive. I mean, if a conductor has positive charge, it must have that positive charge spread throughout it. But in fact, that positive charge will lie only on the surface. Same goes for negative charge. If we look over here at this conductor, and it doesn't matter the shape, all the positive charge will lie on the surface of the conductor, not within it. This is a result of Coulomb's law and the fact that electrons are free to move within a conductor. If we imagine this positive charge to exist due to a lack of electrons, which really that's what it means, because recall our protons cannot move but our electrons can. So this conductor is missing some electrons and therefore it has a positive charge. The electrons that were first on the surface will have nothing acting on them to prevent them from going inside. Because there's going to be, if there was a positive charge inside, the electrons from the surface would go inside. There's going to be nothing pulling them away from it. And so these electrons on the surface are going to go inside the conductor, neutralize the protons there, and leave the protons on the surface to be without electrons, and therefore leave a positive charge on the surface. Similarly, if you were to envision there being too many negative electrons and therefore a total negative charge, the electrons within the conductor are going to repel all of the excess electrons to the edges of the conductor. If you look down here, let's say you have this positive charge, right? And you have these three conductors kind of surrounding this positive charge. The positive charge is going to attract negative charges within the conductor, right? But that doesn't mean that you're going to have a positive charge within the entire conductor, even though there are less electrons within the entire conductor, because the negative charge from the other end is going to fill in the slots within the conductor because there's nothing pulling on it from the other side. Same thing goes for any shape of the conductor. It does not matter on the shape. One more thing to discuss is the effect of a charge within a conductor. So if you notice, we have this spherical conductor, and inside of it, it has a cavity, this kind of gap within it. And within that cavity, there is a positive charge, right? So that positive charge is naturally going to attract electrons within the conductor, and they're all going to go to this surface, right? Now, when they go onto this inner surface of the conductor, now there's suddenly a lack of negative electrons within the conductor. So what's going to happen is the electrons from the surface of the conductor are going to go in and neutralize the inside of the conductor. So the conductor still has an electric field of 0 within it, but now the surface has all these positive charges. The reasons the electrons left the surface and went into the conductor is because they had no protons or any positive charge on the outside attracting them away from the inside. There was just a positive charge on the inside, so that's where they went. Now, the electric field on the outside of a conductor is going to be perpendicular to the surface of the conductor. So if we look over here at this diagram, the electric field due to this positive charge is always going to be perpendicular to our surface, right? At that region, right? Now, another thing you want to notice is the electric field lines here are very sparse. They're not very dense, and so therefore our electric field is going to be rather weak. But if you go to this right side, there's a much higher density, and so our electric field is going to be much stronger. Another benefit of electric field line. So the last thing to discuss is the relation of E&M and mechanics with the current knowledge we have. So we know that a positive charge and a negative charge, or two positive charges, they will exert a force on each other, right? And that force is simply going to be the charge times the electric field. So because we have a force, that means that we can determine the acceleration of the particle. And when we determine the acceleration, we can do kinematics to find out the particle's motion. Another big thing is the electric dipole. Now, the electric dipole consists of two oppositely charged particles separated by a distance d. The electric dipole moment is the quantity P equals QD, and it's a vector that points from the negative charge to the positive charge. Now, the electric dipole moment is very useful to do calculations involving the dipole. So, the electric dipole, if placed within an electric field, is going to rotate until the positive charge is as close to the negative as possible, and the negative charge is as close to the positive as possible. So, we can determine that there's going to be a torque enacted on this electric dipole moment because it's rotating, right? And that torque is simply given by the electric dipole moment times the electric field and then multiplied by the angle that the dipole is within the electric field, right? Now, this torque is acted over a distance. If we find our initial position using theta and then have it rotate to a final position, some torque is acted over that entire distance, which means that work must have been done on the electric dipole. So we can calculate that work by doing the integral of our torque with respect to theta, which is just going to come out to our dipole moment, P, times the electric field times cosine of theta. And the negative is omitted since we wanted to find the work done by the dipole, not by the field. If it's the work done by the field, then it's going to be negative because it's decreasing the energy, right? Now, the last thing is the electric dipole moment is said to have energy stored within it because the potential energy is simply the negative of work. And so it's going to be negative PE cosine theta. All of this torque and dipole stuff, don't worry if it doesn't make the most sense. It's rarely tested, but it's important to have some exposure. So in case it comes up on an FRQ or something like that, you at least have a vague idea of what it is.